Okay, so in this video, we're going to actually start by looking at the whole motive, the whole point of logarithms, and show you why there actually is a need for those, of course. But then look at some exponents that maybe you couldn't solve otherwise and the need for those logs. Then we're also going to examine the natural log graph and look a little bit further at e to the x. We'll begin our journey at least in that realm. Before we get too far, I want us to take a moment to look at our homework packet. So if you have your homework packet nearby, what I'd like you to do is I'd like you to open that up and look at number 22. I'm going to just show that on the screen here. If you were to look here at the top, this is 22, D and E. And I want you to look at those two questions. It says 3 to the x equals 9. And of course, in your own mind, my guess is you're thinking, I know what that is. I can easily say that 3 to the second power equals 9. But then when you proceed to E and it says 3 to the x equals 10, a question mark kind of goes up and you're like, well, I know it's more than 2 because 3 squared is 9, so it must be more than 2. And maybe you might even go so far as to think, well, 3 to the third would be 27. Good. So what does that mean? Then it must be between 2 and 3, and probably lean a little closer to 2. And that, I have to tell you, is an excellent approach in this question, that you understand that it is. But we want to give it a value. We want to actually come up with, how do we describe this number that must fall between 2 and 3, and that obviously does have a value. And let me show you how I know it has a value. If you take a moment to look at the graph of 3 to the x, and you may not recall how to graph that, but think of it this way. When x is 0, that would mean 3 to the 0, so that would place that at 1. When x is 1, that would mean 3 to the first power, so that would be 3. And at x is 2, it would be 3 squared, or 9. Going in the negative direction, negative 1 would mean 1/3, negative 2 would mean 1/9, and negative 3, and sorry, that kind of moved down there. But basically what you're getting is you won't ever actually get to 0, even though this line appears to be hitting 0. You actually are getting infinitely close, but you will never actually reach it. And that is the graph of y equals 3 to the x. Now, once again, we can tell from our graph that 3 to what power equals 9. To answer that, you can look at 9 and you can say, okay, yeah, I can see that, and pan it right down and say, okay, that is 2, and that's easily identifiable by the graph. If you look at 10, you can see that the graph still exists. There is a value. The problem is, and again, we can tell it's between 2 and 3, but how do we note what that value is? And at this point, that's where logs come in. See, they realize that there is, in fact, a value there, but they didn't know how to actually give it a number. Now, there was some later investigation, and they were able to come up with decimals that is a good approximation of that amount, and other forms of mathematics. But for us today, and for what we are doing, what I want you to understand is, first of all, that there is a power somewhere between 2 and 3 that does actually represent that. So if I'm to ask the question 3 to the x equals 10, the actual way that you should answer this is saying, hey, I know that there is a power, and that x is what we're trying to solve for, which would be log base 3, and it's going to give me the value of 10. And this basically represents that value there. That's the entire intention of logarithms, to represent those obscure ones. And so that leaves us with the best answer we can possibly do. Now, if you can actually solve it, like in the one above here, we would not write x equals log base 3 of 9, because we can actually give a value of that. And so I would prefer on the test as well as your homework, if you can come up with it, I want the answer. But in cases such as you see 3 to the x equals to 10, obviously that's the best answer. So I'm going to leave you with that example, because there will come times where you're going to have questions you can't come up with that power. And so you will resort to writing it as a logarithm. I'm going to change a little bit here. Let's look at some questions that we have to solve. 5 to the x equals 125. So If you can do it, I actually want you to come up with the answer. Now, a way that you can actually solve these instead of just looking at them as you see here, but isn't actually to understand that we could write this as x equals log base 5 of 125. But again, I'm hoping you, if you can, come up with those answers. That's what I want. X in this case would be, good. How about 5 to the x equals 8? Can we do that? Well, of course we can do that. What we basically do, again, is since we don't have an exact power, we know that it's more than 1, but it obviously is less than 2. We would write this as log base 5 of 8. Okay, how about e to the x equals 8? Again, we don't know what that would be, but we can write log base e of 8. Now, I'm going to take a quick moment to just talk a little bit about that. Log base e. You will never, ever, ever see log base e unless they're trying to mess with you a little bit. But the truth is what that represents actually is what we call the natural log. And so I tell you that because log base e is actually a more natural. E actually occurs, to use that term, more in nature. It occurs not just in probability. It doesn't just occur when we're dealing with logs. It doesn't just occur in all kinds of mathematical numbers and solving. But believe it or not, it came up with the natural log because it occurs mathematically frequently. And so it's basically more natural. So when we're looking at the log base e, instead of writing log base e, we actually write the natural log. And so this means the same thing. We'll get to more of that in a moment. Log base 2 of x equals 3. So what does that really mean? That means x equals 2 to the third power. Remember, log equals the exponent. So the base is 2, and that's the exponent, 2 cubed, which of course we can solve. And this one here would then be e cubed. And since we don't know what e cubed is, we just simply leave it as e cubed. Great. Okay, so as I said, ln means log base e. So I'm just going to do a few practices with that and how we do that. So if I want to figure out e to what power equals 8, we can't do that. So what we write is the natural log of 8. Again, what does that mean? That means the log base e of 8. So it means the same idea. How about this one? E to the x equals e squared. My hope is that this seems kind of obvious to you. Okay, look at that. E to what power equals e to the second power? Say that again. E to what power equals e to the, well, obviously x equals 2 because they're both the same. How about this next one? E to the x, how could I rewrite 1 over e? E to the negative 1. And so it becomes, again, obvious that x equals negative 1. E to the x equals 2. Can we do that? Well, we can, but we would have to use log base e, or natural log of 2. All right, now, let's look at this a little on the other side of things. What if I give you a log and I want to know what x is in this way? The natural log of x equals 3. Remember that this is really a fancy way of saying log base e of x equals 3. And we said that, hey, logs are exponents, so that must mean that e being the base to the third power, that's what x is. And again, here you'd have log base e of x equals 1. And so this would mean that x equals e to the 1. My hope is that it becomes almost second nature so that when you see ln, that you'll automatically think e to the x.